Okay. So here, let's take that one. Okay, so the uncivilized one, this one looks like it might be civilized.
Right.
Conceivably this.
Mm-hmm.
Okay.
And
Okay, so let's take these, and then we want to ask the question, what do these do? Let's say, well, we can just do it with tables of ones. Okay, so here,
or we can pick out repeated lengths.
well, we
If
can
it
do that in a minute, but hold on one second. Table, K, 6. Then let's take that first one there. Actually, just do this. We need to go a little bit further. What the hell are these doing? Look at this one. Look at this crazy puppy.
uh-huh. Nice.
Well, in a generalized sense of nice.
Mm-hmm.
I mean, okay, so let's look at that one in a bit more detail. Okay,
All right.
so the question is, does it go to a fixed size after a certain number of steps? 1, 2, 1, 1, 1.
For some reason, I think that's acting special on prime numbers.
I don't believe you, but we'll try. Hold on a second. Okay, so they do appear to converge to something.
Okay.
They converge to the all stripies.
Interesting. Can we find out the length of the last one?
Obviously, that's what I was going to do.
And let's add K to the table.
Well, but why is this not stabilizing?
Try just say 10,000.
Let's just try 1010. I don't know why this didn't work. Okay, so let's set up to 100. Let's say 10,000 here. Okay.
Well, that's interesting. And it looks like 10,000 isn't enough. Try changing that to 20,000 and let's see if that changes.
Doesn't seem to. I think there's just a bug with these tops getting cut off.
Okay. Oh, I guess you need just plot range all or something.
Yeah. Okay, so anyway, so what are these values? So I think it's an integer exponent story.
I think so. It looks maybe more complicated. Try copying the first 15 values and popping them into OEIS, see if that gives anything. Okay.
Flatteroo as usual. I wouldn't mind just picking up a few random ones from the middle here. Does it deal with like factors of 2 and things?
Yes. But it can sometimes be easier just to try dividing.
Right. Because these are all even after the first one.
Mm-hmm.
What are these numbers?
Oh, that's bizarre, yeah.
So if we take every other number, right? So every other number is just n plus, okay?
Mm-hmm.
So if we say, so let's see, let's call this sequence. Take SEQ 1 minus 1 steps of 2. It's just that. Take sequence 2 minus 1 steps of 2. We get this curious little puppy. What the hell is this?
Uh-huh, yes. I have no idea.
Wait, don't just give up so easily.
Oh no, and that could be enough. I'm just not immediately seeing an answer.
It's got a bunch of Fibonacci's in it. This is a crazy creature. Oh, did we just get a result over here? Oh, we got a 30 billion sized thing over here.
Oh wow.
All right, while I'm at it, actually, let me just rerun. So that's in the k equals 3 case. There we've got a 13 million result. 12. I'm pretty sure I can run up to 17 here. I might as well do it. Oh, it's at least on up to 16.
Seth has been having fun with his power company. It just sent him a bill for $202,000.
Which
Seth Chandler?
God, but he's in Texas, right?
Yes. So in addition to having no gas, they're billing him $202,000 for it. And it turns out the exact bill is the date.
You can't be serious.
Nope. 2021-02-16, and that's what the bill is. Just divide by 100 for the
Embarrassing. There's a cents, yeah, for the cents.
right.
Okay, listen, let's take a look at this thing. We're still looking at this, okay? What is this? Okay, so this is, again, this is this case here. So this case looks about as simple as they come.
Right, but it's not.
Okay, I want to find some other cases that are explainable, if you understand what I'm saying.
Right.
Okay, so this one here is 3/2 to the n. How
Right.
do we get, what clues does that give us about getting Fibonacci, for example? And this here claims to be 3n plus 1.
Right.
Okay, so let's see what well, that's adding 1 in here. Sorry, this one here. So let's just understand. All right, why is this 3/2 to the n? This is using up 2's. Ed, you're much better at this than I am. I mean, in terms of understanding how to think about it. I'm not a puzzle guy. This is a puzzle problem.
Right. Right.
Okay, by the way, this is stuff we already know.
Mm-hmm. I would try adding one more 1 in the second case and see what happens. That might be the doubling.
Do we ever get pure 1's here?
Yes.
I don't see it. Oh, I do get, yeah, I see we do.
That is 7.
Okay, so let's try this. So let's say in that, let's say cases of that with 1 ...
Right.
That's Lucas numbers or something, isn't it?
Right.
Is that Luke? No, that's 2 to the n minus 1.
Right. Right. Mm-hmm.
Okay, so let's look at what that one looks like.
Try changing the initial condition to 4 1s instead of 3.
I'm not doing 4 1s. I'm doing. Oh yeah, right. I am doing 4 1s. Okay, so that one with let's do 2 1s. Oh, this might be powers. This might be arbitrary powers.
Right.
Okay, so what's that? That's, well, let's just look at total of cases of that.
Right.
what do you know?
There you go.
Okay, so that's powers of 2. Okay, so this one then is powers of 2.
Right.
So then let's understand what, okay, so that's powers of 2. Starting with 1, 1, we're getting powers of 2.
Correct.
So let's try starting with 1, 1, 1. Let's try 1, 1, 1, 1. All right, let's do okay, so that's the next power of 2 up, right?
Mm-hmm.
So let's say take table 1, okay. Let's go 1,000 steps here. And let's say parallel table. Let's say k arrow this. K goes to 10, let's say.
Mm-hmm.
Oh, we're actually competing with that other job, which doesn't make a lot of sense, but that's okay. So wait a minute, what's happening here? So if we start off with K1s, what's this sequence here? So this is, it's taking the binary decomposition, right? Oh, look, we just got a result here. 7 billion was our biggest. Okay, so this is taking the binary decomposition. So actually, I'm going to make a claim here. I'm going to claim that if we look at this number here, maybe that number in binary means something. No, not this number. I mean this number here.
Mm-hmm. Well, each case is either 2 times the previous term or 2n plus 2 the previous term plus 1.
Okay, to get the ones generating something, how do we... Yeah, so we're reading off the data. In the 3n plus 1 case, we're reading off the successive 3n plus 1 elements, if I'm not mistaken, as like here, I suspect if we say cases of this, comma, 1 dot dot dot, and then I say length slash at that, that's going to be the 3n plus 1 problems.
Yes.
Right?
Mm-hmm.
So we're reading off the data in the ones.
Right.
Okay, so here we're reading off the data in the powers of 2.
Correct.
Okay, so this one...
Well, in the ones actually, but they give powers of 2.
Yeah, right. Okay, so my question here is, if we were to start this off with like this, let's say, I'm just trying to get a good,
I don't think you'll need parallel table.
well, no, here. K2, 5, for example, plus 1. And then K goes to 31.
Mm-hmm.
Why did I get this? What did I get wrong here? There we go. What did I do wrong here? 1 plus integer digits K. Wait a minute, there. What am I doing wrong here?
Do you need the length 5? Oh, all right, that's okay. Yeah, I see.
Well, it's basically telling me that 1111 never occurs.
Oh, yeah, that makes sense.
What did I get wrong here? Oh, did I just not give a number of steps?
Yeah, that's what I was about to say.
Okay, so what's this doing? So 5,
Seems to like the number 11 a lot.
okay, come on, we can figure this out. Um,
Four, 6, 12, 14. It's mod 8.
no, hold on, let's just do this. Let's say
You've got blanks for 4, 6, 12, and 14, though. Yes.
okay, so find sequence function here is giving to what extent is this the binary decomposition of the numbers? That's my question. I think it's related to that.
Yes, I believe so. You're right.
But let's figure out, okay. Okay, so the guess would be that this is powers of 2. But I mean, if we take one of these and we look at its ratios, well, actually, we can just see what it is right there. 1 goes to 3 times 2 to the t plus 1, otherwise known as 6 times 2 to the t.
Right.
6 times 2 to the t minus 1 for that one.
Mm-hmm.
As opposed to 3 times 2 to the t minus 1 for the 0 case.
Right.
And the case where we start with 2 1s is here, Oh, this is always length 5. Right, so the case we want to look at here is this one here, where we say 1, 1, 2. Okay, now we'll say 2, 1.
Mm-hmm.
Now we'll say 2, 2. Oh my gosh. And now we'll say 1, 1. Do you understand that?
Oh, we've seen that one before.
No, this one is the one we already did.
Right.
The question is, what is it changing? Okay, I need a piece of food. Think about this for a minute.
Okay. All right.
Okay. Hi. Figure it out?
Oh, if you look at the places where there's blanks, it's mod 8, it's 0 or 4. Above 16, though, it goes to mod 8, 1 or 3. So I bet if you went to beyond 32, you'd start seeing different behaviors with different number of integer digits.
Wait a minute.
But all the cases are basically the previous term times 2 plus 1.
That's crazy complicated. All right. Let's see if we can get another interpretable computation.
Okay.
I mean, can we get powers of 3? This is always going to be a positive 2 story.
Yeah, I imagine if you do 2 goes to 6 ones, you'll get powers of 3.
Yes, I think I should have an idea here. Oh, for goodness freaking sake. These animals are just too damn smart. What is that? What the hell is that?
It's 2 times, yeah,
Oh, it's 2 times 3 to the power t minus 1. Okay.
right.
Well, so this is very close to powers of 3.
Oh, try doing 3 ones as the initial condition again, now that you've added more steps.
I think it's going to
Hmm.
take. I think it's going to take 6 ones, but I'm wrong. That's crazy. Okay, so let's. What about putting a 2 in there just for good measure? How about 2 2s? What are those sequences?
It's 3n plus 2.
That's a recurrence there.
Hmm.
I don't think so. It's 4n minus 3.
Okay.
Oh, but it is. It's 4 times 3 to the t.
Right.
Okay. How do we get a pure power of 3 then? What about the possibility? Oh, here's an idea.
You could try 1 goes to 2 2 2. There's probably some adjustments to the 1s and 2s.
Well, what about triangular numbers? That seems like another thing we should be able to get.
Hmm.
Um, so the question is, two, I get pure powers of 3. So what we've got right now is 3 parameters. We've got a table of the number of 2s here,
Right.
table of the number of 1s there, and a table of the number of 1s here. Assuming that's enough, and we don't need that. Okay, so now let's do parallel table.
You might build a add find sequence function right on top of it. And I'm gonna go see what my dog is getting into. And I'm back.
There are no occurrences. I'm pure puzzle.
It's okay.
So,
Interesting.
well, the other possibility is to look at that. Let's do the following. We could use parallel try potentially for this, but let's do this. Okay, so instead of table 1C, let's make a table integer digits. Oh gosh, how do we go? We want the sequence of tuples. Well, and how do we make a series of numbers? Well, here. I put n first, right? The index n first before the 2 to the n minus 1, like that, right?
I always check.
Oh, wait a minute, that's a C. Oh, this. Okay. 3, 9, 27, triple blank. Okay. Well, none of those are powers of 3.
Right. On the bright side, powers of 4 will be easy.
Do these grow approximately like powers of 3? I mean,
That's what we saw with the previous cases.
oh, for God's freaking sake, look at that thing.
Mm-hmm.
So it's roughly 3/2.
Right.
Well, Mr. Post.
Obviously, you should be eating post cereal.
What I'm hoping to do is to post my post. Okay. All right, well, let's go back. So we don't quite know how to do powers of 3. We can do two times powers of 3. You know, the other possibility would be to pick up something other than the ones. See what I'm saying?
Right.
And
Like converting it back into an integer, subtracting 1 from all cases and converting back to an integer digit.
well, this was 6, right?
I think so.
So by the way, we do it with 5. And 4 gives us powers of 2. And 3 gives us the ceiling of powers of 3/2, right?
Right.
So most likely, if this is the ceiling of powers of 3/2, this is powers of 2. I wonder if this is the ceiling of powers of 5/2.
I bet you're right.
I'm not so sure I'm right. And I'm wrong. Let's check this case.
Okay.
It was starting with That same initial condition, right?
I think so.
Okay, so this isn't right either. So this is wrong as well. Maybe, oh yeah, it's just full of nonsense. Wait a minute, what's going on here? 1 goes to 2, 2. One goes to 2, 2. 2 goes to 1, 1, 1. Look, that 27 is different.
Okay.
What the heck? Oh, very different. Look. That wasn't 3 halves to the n. It was the nest list of ceiling of 3 halves.
Okay.
See what I'm saying?
Right. There you go.
And that's not the same.
Yes.
Okay. Let's look. I think this one is understandable.
Mhm.
Okay, I think let's look at this guy and how this guy actually works. Okay.
Mhm.
So that's the next one up. But now this one, if I were to go like this, I don't think infinity is a good idea there.
No. Oh, that looks familiar.
What do you mean it looks familiar?
It looks like some of the ones we've been working on.
Well, 2, 3. All right, so let's do this. Let's say that thing, table K.
The next interesting case will be 25.
What's our TS? Oh, TS evolve list.
Oh, these will all be 1. You're doing the length of the last item. So it's and they all terminate, so you're just going to see a bunch of 1s.
No, I'm not.
Oh, right. That's right. You get a different thing. Okay.
What is that? Oh my God.
All the even values are 2 times the integers.
I know that. What about the odd ones? It's the same as that thing above.
Yes. I think the numbers are different though.
Yeah, I think so.
Up above you divided by 3 or by 2.
I know. But here, okay, I wonder what would happen if we just did this. Oops. Boring. Oh, it's probably obvious that it has to be of the same. Okay, so if one of these is longer and one is shorter, so that's going to be basically 3m plus 1. Although it's a modified 3m plus 1, I think. Is that exactly 3m plus 1, or is that something different?
Looks different.
What's that?
Looks different. Oh, it looks like I guess that's the same.
It's not the same. It's a different recurrence.
Okay.
Okay, so then can you investigate these some more? I mean, we're looking for ones.
Sure. Email me that notebook.
I will, but hold on one second. I mean, I'm I wonder what other cases are even tolerably simple. Do you think this thing terminates? Yes, I think it does terminate. So I think this one, let's just see what it does. It's going to be, okay, so what we want to do is we want to find the cases of ones here. Wait a minute, why does the other one actually terminate? This one looks very much like it's, okay, so this one, what is the relationship between 19 and 9? Here, this one here. Okay, 19 to 29 is strictly 3n plus 1 over 2. Is that correct? Ed? Hello, Ed.
Yes, I believe so. Yes. Yes, it is.
Okay, now doesn't the actual 3n plus 1 problem then loop after it gets to 1?
Yes.
So it's a non-looping 3n plus 1 problem.
Right. The other case might be 3n minus 1.
Okay, so here, this case here you're talking about?
Yes.
Okay. Nope. What's the relationship between 9 and 19? Nine and 19.
I'm not sure.
There are two attractors here. Right, there's
Right. Uh-huh.
a
A loop and a terminator.
the termination. Seven goes to 3. What's that relationship?
Oh, it's n minus 1 over 2. If it's odd.
Okay, n minus 1 over 2. Okay, so if odd q of n minus 1 over 2. All right, let's look at the even case. If it's even, what is it? Is it 2n minus 2? Nope. 3n over 2.
Looks like 2n minus 6.
Check another one.
Let's see, 12, 18, 6, 9.
No, it's 3n over 2.
Okay, that's right. Yep.
Okay, so this is, so if even q, 3n over 2, otherwise n minus 1 over 2, which is just slightly different from okay, so here we start off with, like, let's say 14. Okay, well, this is another one then what we've got. So this one here is this.
Right.
3n over 2 and minus 1 over 2. So it's another recurrence. So again, how would we get a Fibonacci? We've got powers of 2. Let's remind ourselves how we got the powers of 2. We got the powers of 2 by saying 1 goes to 2, 2, 2 goes. So I'm going to predict that the path to Fibonacci, question mark Fibonacci. Okay, so here I'm going to predict is a 1 goes to 1, 2. Is this ever going to do anything? Is this going to do nothing? Okay. Okay, 1 goes to 1, 2. How about 2 goes to 2, 1? Is that obvious that that does nothing?
Yeah, because you're chopping off 2 each time, so it's never going to grow.
And that might not have a 1, 1, 1 sequence in it. What happens if I go to 10,000 steps here? Oh boy, it terminates. Well, it's nice that it terminates. What are those? It terminates in 1 step on every even number. Oh, look. These are going to be, if I take the differences here, let's go up to, let's say, 20,000 parallel table. Oh, for goodness sake. What are these? What are these again? This is something meaningful, I think. Let's see, I want to go like 11 or something there. Oh, was that our thing from above?
I think so.
1, 2, 1, 1, 1. Yep, that's the one from above.
Okay.
Okay, but so that one has only a finite number of ones that it generates.
Right.
That's a clue. So for even numbers, it just terminates after 1 step.
Okay.
Or at least it doesn't generate any more.
Right.
For odd numbers, this is what it's doing. So let's look at another odd number. Let's look at the number 111. Let's not look at number 111. Let's look at 41. Okay. So this is, let's look at like 21. Okay, so something is happening here that is having some number of iterations.
Right.
It's essentially what we're seeing here. So 3 is 358. 5 is just 5 and 8.
Let's try to do the one with 7 for more steps.
Which one was 7?
Oh, it terminates. Now, I guess you don't get more steps.
Yeah, no, this is it. All right, this is our final act. This is the last one we're going to try and do. Let's see if we can nail this one. Okay, so let's just get more data here. While it's computing, let's go to 100,000 steps. And let's go K, and we'll just do odd numbers. Okay. And we'll say parallel table K arrow. Right, we only need to do odd numbers, correct? Right, because the even numbers were trivial. Right,
Right.
Ed?
Right. Mm-hmm. Oh, sorry. Right. Yes.
Look at that little puppy. What does that remind you of?
It's a powers energy, right? Energy exponent, right?
Okay, hold on. We need to get this. Okay, so hold on. Let's look at a nice long sequence here.
I found it.
What? That's not very helpful. What did you find? What?
I posted it in chat.
Is that Audrey Terrace? I remember her. Is she still around? Is she still alive? I gotta see.
You'll notice that some of these sequences are copied right into this.
I should put her in my list of people to send this post to.
Wolf Dieter Lang.
Who?
That's the author of this sequence.
No. I was Audrey Terrace. I remember her from a long time ago. Okay, so how? What's the code for this?
For example, one part of what you found with the parallel table is 15, 23, 35, 53, 80. And that's part of the sequence earlier is 7, 11, 17, 26. A lot of the portions of your tables are wrapped up in here.
Okay, but this is modified collat sequences. So what are those modifications?
I'm not sure.
Well, right, but that's what we have to figure out. So these are integer exponents, right? So
Yes.
okay, so integer exponent n2 table n, 20, 200. Okay. So the lengths of these things are integer exponent of n,
Right.
right?
Mm-hmm.
Okay, so what are those numbers? The length is the integer exponent. So the integer exponent is the number of zeros at the end, right? Now, how can that be? Wait a minute. It's not the number of zeros. It's the integer exponent. Wait a minute. The integer exponent of 7 is not quite the integer exponent. Okay, so this is the clue, right? So for this, 1 goes to 1, 7 goes to 4, 9 goes to 2. So you understand that this isn't exactly integer exponent because the integer exponent, right?
Right, right.
So what numbers are the low ones? The low ones are 5, 9, 13. So they differ by 4. Do you understand what I'm saying?
Mm-hmm.
So this is, how about, what's the integer exponent of n minus 1? N plus 1? No. Okay, why would 95 have a big value here? Okay, let's be precise on what these numbers are. So if I say here, okay, what integer exponent of 5 gives 2? So, I mean, these things, notice that the alternating numbers, okay, they alternate between, so that's a value, right?
Right.
Well, it seems like mod 4, there's something mod 4. Okay, come on, we can do this. Okay. The case of, okay, the one's case was just increasing, right? The even numbers here.
Let's look at the second value for each of these.
No, wait a minute. I've got an idea. Look at this. Watch this. Watch this. Watch this. Watch this.
The second value is increased by 3 each time.
Okay, look at this. This is incredibly close to the integer digits function,
Right.
including all these things, right?
Mm-hmm.
Okay, let's compare it with the integer digits function. Okay, so let's say values. Okay, so now well, first of all, let's add 1 to this thing. Wait a minute. It is the integer digit function, but it has been, okay, hold on. Integer digits of 1, 1, 3. No, plus.
Right.
Is that it?
Uh-huh. Except for the first term, yes.
Okay. Okay.
And
So
also, if you look at every second term in your values above, you get increases of 3.
what do you mean increases of 3?
Do every second term in the
What? This?
right.
Well, here, okay. So this 5, 8, 11, 14, 17. Okay, what about the third term?
Looks like it increases by 9.
Relative to what?
Relative to
What?
the term before.
Which term before? 17 doesn't have a term before.
It skips 2.
What do you mean it skips 2? It skips back to here?
So it's 8 skip plus 9 skip plus 9 skip plus 9.
I don't understand. So you're saying this 17 is derived from the 8 back here.
Right. And the 26 is derived from the 17. And the 35 from the 26.
I'm totally confused. So what's the formula for this? I mean, like if I take one of these here and I say differences of that, what the hell's that?
Those are the last one is 3 to the 5th. This second to the last is 2 times 8. 2 times 3 to the 4th.
So what? I mean, so what's the formula for these?
Oh, the first the long one, 95 near the end, it ends with 729 minus 1. It would probably take me 15 minutes to figure out exactly what this is.
Okay,
But it's based on powers of 3.
I'm sending it to you.
Okay.
Um, okay, and I will send you this whole notebook as well.
Okay.
And then, okay, so just a couple of minutes on ABC and then we're wrapping.
Okay.
Okay, so where was our ABC calculation?
I sent an email, but I can copy the relevant part. And that's boring. There's a table near the bottom of there. That's the interesting table.
So what is A plus B equals C?
That's the ABC conjecture. Basically, you want that condition met, and then you want the rads to work well, and that means you've got relatively close powers.
No, I understand, but what is the precise thing that we're dealing with here? We're dealing with
Well, for us, we want things like 2 to the 3rd plus 1 equals 3 to the 2.
2 to the 3 plus 1 equals 3 to the 2.
Which is the Catalan conjecture. And this is the sharp attractor for the 3n plus 1 problem.
Okay. The Catalan conjecture is that that's the only case where A to the B plus 1 equals B to the A, right?
Is the only place where there's 2 adjacent powers.
Oh, I see.
Proved in 2002.
Well, that's not a conjecture anymore.
Right. But it's still called Catalan's conjecture, even though it's proved.
Okay. All right. So then so why is this relevant to the 3n plus 1 problem?
Because when 2 powers are close together, you can get a cycle in something that is Collatz-like.
Yeah, but what I'm trying to get is something where the thing used per step, right? So what we want is A to the power n. What do we want? We want A to the n, but we've got these ABCs, A plus A n plus B for various A1 plus B, AI plus BI, AIN plus BI, right?
Right.
So the product of those, and then we've got a modulus plus modulus.
Right.
M. Okay, so what we're going to get is a product of, we're cycling around for a product of the AIs. Okay. Product of the AIs for I up to M divided by some power of M. And that power is going to depend on the B sub i's.
Right.
Right, so that's our and we want that to be equal to, we'd like that to be very close to 1.
Right.
Perhaps equal to 1. I mean, so for the 3n plus 1 problem, to be clear, the analogous thing for 3n plus 1 is 3n plus 3n, which happens to be plus 1, times we're ending up 3 over 2 times 2.
Right.
3 over 2 squared.
Uh-huh.
And so in this case, so part of the issue is divisibility, right? Of product of AI plus BI, this thing here will be divisible by, for some of those, it's divisible by m.
Right.
Right? Now it's divisible by n for some is divisible by m for all n, right? It has to be. Otherwise we
Right.
couldn't do the division, right? So then the question is, okay, so for what's the condition that this is divisible by m for all n? Answer that the AI and BI are both divisible by m. Is that right? No, that's not right, because 3m plus 1 is always divisible by 2.
Right.
So what's the condition?
You want the log 2 of the power to the 1/3 or some other.
Wait a second. There's a different issue. This n is not an arbitrary n. Okay, that n is AI times something of the form m times k plus whatever we call it, right? Plus j or something,
Right.
right? Plus b sub I, because we're saying that that is divisible by m.
Right.
Right? So trivially, that term is divisible by m.
Mm-hmm.
So the issue is, if we have terms, okay, so in fact, we could just say, it's actually, this is the ith term, and we're saying that a sub I times I plus b sub I needs to be divisible by m.
Mm-hmm.
Right? So for the 3m plus 1 problem, the corresponding terms are 3 times 1 plus 1, that's 3m plus 1, turns into 3 plus 1. Wait a minute, that's the 3m plus 1 term. Oh, and then the other term is even, so it's already divisible, so it's just 2, basically.
Right.
Right? Okay, so what's the next one of these, which has this property that it's got? Do you see what I'm asking?
I'm not sure, because I was when you recur these, you basically run into powers, and that's the issue I was looking at.
Oh, I know. But look at this, because this is going to tell you how many. Look, it's going to tell you how many powers. Look, because this thing, every time it's divisible by m, if it's divisible by m to the p, for example, right? If this, okay, if
So
a sub I, wait a minute, times I plus b sub I is divisible by m to the p, then that's going to give you the pieces of this product here.
okay,
Right?
but those also have to be powers, or something close to them.
No, but look. So what we're going to get is, so in the 3m plus 1 problem, what we've got is the AI BIs. So A for I equals 1, that, well, actually for I equals 0, Okay, so this is the cases for I equals 0. The values are there's an n there, right? So the value, it's 1 and 0. For I equals 1, the values are 3, because that's odd, and this is 1. Okay, so this is 3 and that's 4, and that's why we get to divide by that, right?
Mm-hmm.
Okay, so what's the next case of this? So what we can do is we could just enumerate, right? Here, we can just be enumerating. So what are the corresponding things? So the weight of this, because this is a 2 thing. Okay, so let's make a table for the case of let's say mod 3. Okay. So then mod 3, mod 3, what do we get here? Mod 3, we're going to get okay, the question is, how many powers of m, how many powers of 3? Why can we divide this one by any, powers of 2 in this case? So we don't get to divide this. Oh, I'm confused. Do you understand what's going on here?
Not really. I thought you were closer in your notebook where you're discussing it, because when I was looking at that, I realized there was an ABC conjecture
No.
shortcut.
This is relevant. This is relevant. This is
Well, let's grab the table that's in the other notebook and copy it over onto this.
Which other notebook?
The RAD notebook, the best case examples, the high value, high. Just copy that.
Okay, Ed, let's go through this again. Okay, this is not that hard to understand. All right, so
the third from the bottom is why the 5n plus 1 problem is closer than the 3n plus 1 problem in your notebook, because when you do the same sort of experiment, you get closer to being fair, non-biased, and it's because of this particular special example, which is one of the best known cases for the ABC conjecture.
all right, but let's just enumerate what. Okay, hold on. So let's do the 7n case, okay? Let's do the mod 3 cases, right? What do the mod 3 cases look like? Okay, what are possible mod 3 cases?
Right, and if you look in that table, it's the ones where you have high powers of 3 is where they'll work really well.
I know, but Ed, what are the possible cases? What does it even look like? It basically says mod n comma 3 comma 1, and then it's computing. What is it actually computing? The 3n plus 1 problem is computing. Let's see, how did I formulate it here? Okay, well, here I did it like this, but I could have done it with a divided by 2 on this thing here, right?
Right.
And that would have gotten me a different length. But let's assume that I did that. Okay, so then what I've got is, if in the mod 3 thing, I have purely n, okay, then I have a1n plus b1, and then I have a2n plus b2, right?
Okay.
So my question is, what are the possible values of the AI and BI such that these things will be divisible by 3?
Right.
Okay.
And I believe it's going to boil down to the 6th case in the table.
Hold on. Let's just enumerate. What are the cases for which, what are the values of A, B, A2, B2, such that for this n, okay, so let's imagine that in this case, n is of the form 3k plus 1. Okay, so what does this look like? It's A1 times 3k plus 1 plus B1, right? That's
Right.
what it is. Okay, so now for what? Okay, so this is that term. So that means that A1 plus B1 has got to be, i.e., implies, A1 plus B1 is divisible by 3,
Mm-hmm.
right? So this one here is going to say 2A2 plus B2 is divisible by 3. So the condition is that A1 plus B1, in fact, in general, A1 plus IBI, AI plus IBI is divisible by the modulus. Okay, so let's say the example of this is I up to 2. That's the case. Both of those have to be divisible by 3. In the case of, in the 4 case, well, let's say in the 4 case, those have to all be divisible by 4, right?
Mm-hmm.
So what numbers AI, BI, A2, B2 will be divisible by 3?
Right. Or powers of 3.
Yes. Okay.
So
Right.
you want the 5th and 6th items from that high table.
I don't understand that. So just tell me the values that I have to have it, because these values, right? What values do I have to have here?
Perfect powers only work with the 3n plus 2 case, and you get kind of close with the 5n, which is
Oh
the
no,
3rd from the
Ed,
bottom.
Ed, look. For what values of AI and BI are these divisible by 3? Okay, so I could just do, let's just make, a very stupid thing. Let's go how do we do this efficiently? Well, we can just say, let's say select this. No. Okay, here we go. We could just say select. What am I going to use here? Can I use tuples? What should I use? I could use tuples of range of 0, let's say 4 or something, comma 4. And then I want to select from those tuples the ones for which divisible q. Which way around is divisible?
I don't remember.
N is divisible by m. Okay, so n is #1 plus #2 is divisible by 3, and divisible #3 plus 2 #4 is divisible by 3.
Right.
How could this be right? Oh, they're all 0. That's not very interesting. Okay, so what's a case of this? So let's say 4214. Okay.
Mm-hmm.
So then what's the analysis of the average? So in 4214, we're asking 4 and 2 is divisible by 3 once. This, let's see, we want the first element plus the, do you understand what I'm asking?
Uh-huh. And
Okay.
ultimately, since you want this to be unbiased, the adders don't matter. The only things you really care about are the multipliers.
I know, but I see. So you say, but to know how many powers we divide by depends on the adders.
Right.
Okay, let's write this out in a more sensible way. So instead of, so what I want to do is I want to write out, let's say each pair AI, BI, okay? So let's say I write, so let's instead do, this here, and let's say take list. Actually, I just want to partition this into twos. And while I'm at it, let's write this for general modulus M, okay?
Mm-hmm.
So for general modulus M, that's 2M. Is that 2M as well? I think it is.
Right.
Okay, so then what we want to do is we want to say select those for which it is the case that divisible, let's say map indexed of divisible hash sub 1 plus hash first of hash 2 times hash sub 2 comma M, and then I want that map indexed mapped over each one of those, and then I want to take that and I want to add that. Okay, and I want to say ampersand that. I don't know whether that ampersand does the right thing there. Yes, it does. Okay, so now we say with M equals 2. Oh, come on. Oh, no, I don't want to do that. I want to say, no, that's for each tuple, right? Each tuple there. This is mapping over the tuples. This isn't right. I don't want this. I want each one here to just go up to M. Is that right? No, that's not right either. I want, hold on, what do I want here? I want, do you understand what I'm trying to do?
No, not really.
Oh, come on. Okay, so look, we've got AI and BI. For each one, this is A1, B1, A2, B2.
Okay.
And I want all choices This is wrong. Why is it range 0 to 4? That's wrong. This is right. Okay, so hold on. Oh, come on. Why is that not right? Oh, maybe I need to say modulus 3. No, modulus 2. Okay, this should give me the 3m plus 1 problem, okay? So let's walk through this again. So each one of these AI come on. How does this work? Okay, do you understand what I'm trying to do? I'm trying to say for any given value of the modulus, for any given mod there, right?
Right.
I've got this form here.
Mm-hmm.
Okay. So then I'm trying to say, what are the possible forms of the AI and BI? Okay.
Right.
And those possible forms simply go up to the modulus, the value of the modulus. Those forms, each one of those forms is from 0 to the modulus minus 1.
Right.
No, that's nonsense. Because 3 is, it's mod 2, but we go up to 3. So I'm saying we're going up to 1 more than the modulus.
Mm-hmm.
So actually, we probably could even go up to m plus 1 here. And then that might conceivably be right. Let's take a look. 0. Oh, come on. Okay, so this is each pair AI BI. Okay, what's the condition on the AI BI? The condition is wait a minute. The condition is that this thing, this AI plus in that modulus, hold on. So we're mapping over this. And for each piece, okay, so let's take a look at this. So for each piece there, we're mapping over something like this here. Well, that's kind of nonsense, isn't it? Let's say, okay, divisible by, why is it saying 4 there? Okay, hold on. Why is this giving this result? This is saying hash sub 1, it's mapping over this. Okay, map indexed over these. What happens if I say it level 2? Oh, for goodness sake. Okay, help me out here. Help me out. Look, we're looking at, this is the A sub I plus What the heck is this doing? Okay, what am I being stupid about? Why does that say 4 there? Hash sub 1 should be 2, shouldn't it?
Yes, there's
Oh, plus, but. Oh no, this is right. This is right. Plus first of hash 2. This is correct.
so for the A1, B1, they have to have a different modulus mod 3, but not 0. And for A2, B2, they have to have the same modulus mod 3, not 0.
All right, you're going to work this out. Work this out, okay? Just get an enumeration of possible systems and their, exponent story.
Right, that's going to be a simple case, though. What we need to aim for is the ones in the ABC conjecture here.
No. I want to enumerate all the cases, right? So in other words, if I take a case, right? So let's say I've got
Right,
in mod
and
3,
I can rank those simpler cases for you as terms to bias. However, if you want an unbiased case, that's not going to work because
okay, fine.
your
I just want to
orders of
compute.
magnitude away.
Wait. I understand that. I want to see the case. Okay, so let's look for a given. Let's pick for mod 3. Okay, for mod 3, we've got let's just say we've got this is a mod 3 case. We've got the some random thing here, right?
Mm-hmm.
2, 3, 1, 4, let's say. Okay, that will be a mod 3 case. And so in the case of mod 2, the 3n plus 1 problem is specifically 1, 0, 3, 1. Correct?
Right.
Okay. That's 3n plus 1. Okay. So what I want to know is, okay, well, maybe this is the better way to do it. Given something like that, right? What is the weighting factor, right? The weighting factor depends on, okay, so given the modulus, right? So weighting of the list, okay, so a list here. So
Mm-hmm.
that list is of length m. So with m equals length of list, right?
Mm-hmm.
Okay, so what we do then is we say, okay, so this one here is divisible by 2. So we want to take, is it a simple, no, we're taking the sum, but it's the sum where this is 1 times that, and the next one will be 2 times that. Right, it's this.
You can basically ignore the second part because you're basically going to aim for even numbers.
Not right. That's not right, because this is going to, the whole point is there's an extra factor. There's an extra factor of 2 that comes because this is guaranteed even.
Right.
Okay?
So this is basically 3 halves there.
I know, but the whole point is to compute that. And so what I'm saying is you want how many powers of the modulus are in, it's the integer exponent of the modulus in each of these pieces. Right?
Mm-hmm.
Okay, so let's work that out. So it's this. Okay, so it is each one of these. So let's say it's map indexed of hash sub 1 plus hash first of hash 2 for the map indexed of hash sub 2. Right?
Right.
That's okay, so that's mapped onto list. Okay?
Mm-hmm.
So that's going to give us, and so then for each of those, we want to map integer exponent of m onto that. Do you agree?
Mm-hmm.
Okay, so in this case, the weighting here will be, if I say weighting of 1031, by the way, I think I got wrong. I think this is #2 minus 1 there. I think this is, am I not right? First of #2 minus 1, I believe.
Okay.
Okay, there we go. So that's the weighting. So that tells us okay, so wait a minute. Why is that integer exponent 2? Why isn't it 1? Oh, because that's, well, I think that's right. You get to divide twice. No, explain, help me. Help me. Do you see what I'm asking? So this is a sub n, so that's just n, but that's the case where we know that n is of the form m plus 0. You see what I'm saying? M, that's the modulus, that's the case where the modulus of m, modulus of n mod m is 0.
Right.
So we know that divides. This case, the modulus is 1.
Mm-hmm.
Right? Okay, so tell me how we should compute this. Do you understand the question?
Right. I thought you had it before with 1/2 and 3/2. Multiply them together and take log 2 of the product.
No. Look at this thing. Look at this. We're trying to work out. Okay, this thing here is the thing where we know that n is equal to 0 mod m. Okay? Here it's equal to 1 mod m. Okay? In the case where it's 0 mod m, we know there's a single factor of m.
Right.
In this case. So how do we compute how many factors of m there are given those weightings? Do you understand what I'm asking? How many factors of m are there if n is of the form k times m, right? In this case, there is one factor of m, right? Whereas in this case, there is a factor of 4, right? Not just a factor of 2, but a factor of 4.
Right. Mm-hmm.
Okay? Now, we also need to guarantee that these things, I'm very confused, that these things are going to be divisible, that the results from each of these are at least divisible by 1 power of, do you get what I'm saying? By 1 power of, no, this is wrong. Okay, you get what I'm saying? It's got to be divisible by at least 1 power of m.
Right.
Each one of these, we have to pick values such that it is divisible by 1 power of m. Okay?
Right.
So to get that value, the ith one of these has to be such that m times, okay, so m times a, no, a plus the ith one of these times b, that has to be divisible by m.
Okay.
But that isn't right because this isn't correct then. Do you understand? You understand why it has to be this way, right? You can figure this out. I'm going to send this to you. You figure it out. You understand what I'm talking about, right? There's a certain set of vectors here that are permissible.
Right.
For a given m, there's a certain set of vectors that are going to work.
Mm-hmm.
Right? Okay, so find the possible sets of vectors for a given m that can work.
Right.
Then find their weightings. and then we can do all this other stuff. Okay, that's what we have to do.
Right.
Okay, I'm going to go work on this other stuff, and I'm sending you this notebook.
Okay.
Excellent. All right, and we got a few bits and pieces here, but so let's figure them out, and we continue tomorrow. Okay.
All right. Sounds good.
See you later. Thanks a lot. Okay, bye.